Hello everyone, having looked at the role of quarks in beta minus and beta plus decay, we now turn our attention to alpha and gamma decay. And once we've done that, we're going to have a look at the properties of those four radiation types. So let us begin with alpha decay. And a very typical alpha decay would be that of uranium 238, which decays into thorium and the alpha particle. We now know the alpha particle to be a helium nucleus. So we know that by looking at the emission spectra produced from the alpha particle, comparing that to the helium atom, noticing that they're the same, and we'll study that when we look at the composition of stars. Now, when we did beta minus and beta plus decay, I went through a lot of conservation laws with you. Weren't strictly necessary, you won't be examined on them, but just useful in setting that kind of wider context. I'm going to do exactly the same here. So let us have a look at baryon number. Now we're talking about nuclear decay. So it's about the nucleus, neutrons and protons. So the baryon number is the number of nucleons that are in the nucleus. So we've got 238 nucleons in uranium, 234 for thorium, and 4 for the alpha particle. So 234 add 4 give us the 238. So we've got conservation of baryon number. Now, you do need to know conservation on be able to apply conservation of charge. Charge is from the protons, so that's the atomic number. So we've got 92 protons in uranium, 90 in thorium, 2 in the alpha particle. 90 plus 2 give us the 92. We had conservation of charge. Leptons are electrons and neutrinos, so uranium nucleus doesn't have any leptons, neither does the thorium nucleus, neither does the alpha particle, so we've got 0 lepton number on both sides. In other words, all of our conservation laws are being obeyed here. Let's just have a look at momentum though. This is a conservation law you do need to be able to apply. We know that initial and final momentum are equal to each other. So what does that mean in this context? So here's our uranium nucleus, and initially it has 0 velocity. And so that means it's got 0 initial momentum. That means that the thorium and alpha particle that are produced must also have 0 final momentum. Now, the alpha particle does move off with some velocity, and presumably the thorium nucleus recoils back with some velocity, and the length of the arrow obviously indicating that the velocity of the alpha particle is much greater than the velocity of the thorium nucleus. And that makes sense based on their mass, doesn't it? So the alpha particle and the thorium nucleus must have the same amount of momentum, but moving in opposite directions. So when we add them up, they sum up to 0. Now, in reality, the thorium is part of a metallic lattice. It's not actually going anywhere. I guess there's that increase in kind of vibrational energy. That's the form that momentum is seen in. Okay, is it possible to compare the velocity of the alpha particle with the velocity of the thorium nucleus if it were free to move? Momentum is mass times velocity. So we've got 234 atomic mass units of momentum in the thorium nucleus. Don't worry about the atomic mass unit. We're about to look at it. Multiplied by the velocity of thorium is equal to, we've got 4 atomic mass units for the alpha particle multiplied by its velocity. So in actual fact, the atomic mass unit cancels out anyway. So this is telling us that the alpha particle moves off with a velocity which is 234 over 4 times greater than that of the thorium nucleus. And if I work that out, that comes to about 60 times that of the thorium nucleus. Okay, so that's applying our conservation of momentum. If the thorium nucleus was free to move, it would move off at a speed which is 1/60th of that of the alpha particle, and that's down to the difference in mass between the two. So that's alpha decay. In terms of gamma decay, there's very little to say. Gamma is energy. It's part of the electromagnetic spectrum, and there are no baryon, charge, and lepton numbers to conserve. The reason for gamma decay is when we have a nucleus that has too much energy and it needs to offload, it needs to get rid of some of that energy, and that's where the gamma comes in. So very little more to say about that. So I would like to put it all together now by just looking at the properties of alpha, beta minus, beta plus, and gamma. And I can't remember if in your packs you've got a table to complete, but I'm going to go through the properties and then you're going to complete a table summarizing all the main properties for the 4 different types of radiation. Okay, we've got to compare 2 forces in the nucleus. The strong force and the electrostatic repulsive force. And that's going to determine the stability of a nucleus. So if that repulsive force is greater than the strong force, then the nucleus is not going to hold together. It's going to be really unstable. Now, comparing those 2 forces is obviously not entirely straightforward because the properties of them, they're different. So in terms of range, we know that the electrostatic force operates over an infinite distance. It's a long-range force, whereas we know that the strong force operates over the diameter, the dimensions of a nucleon. It's a very short-range force. We know that the electrostatic force is weak by comparison to the strong force, and we know that it operates over different particles. So the electrostatic force is the force of repulsion between 2 protons, but the strong force is a force of attraction between neutrons, neutron-proton pairs, and proton pairs. So comparing those 2 forces is not entirely straightforward, but it is the comparison of those that determines whether or not a nucleus is stable or not. So reasons for a nucleus not being stable, too many protons. So then the electrostatic force would dominate and that nucleus would fall apart. It would be unstable. Too many nucleons in total. So as you add protons in, they affect all the other protons in the nucleus because of that long-range nature of that force. But if you add nucleons into a nucleus, so let's say we add neutrons into the nucleus, then the interaction is only between neighboring neutrons. Okay, so the way that those 2 forces increase is going to look very different. And finally, it could just be that the nucleus has got too much energy, and so it needs to get rid of some of that energy in order to become more stable. And that's what radioactive decay is all about. It's an unstable nucleus doing something to become more stable. And the doing something is alpha, beta minus, beta plus, or gamma, or a combination of those events. So let me just remind you of 2 ideas that you've come across already at GCSE. Radioactive decay cannot be predicted. And that's what we mean by it being random. You cannot look at a nucleus and kind of go, right, if I come back in 4 minutes, it will have decayed. But if I come back in 3, it won't. There is no indication as to when a nucleus is about to decay. All you can say is that within a given time frame, there is a probability, there's a likelihood that it either will or it will not decay. Equally, radioactive decay is spontaneous. In other words, all of those kind of external conditions that you could change that work with a chemical reaction do not apply here. So increasing temperature, increasing surface area, increasing pressure have no impact on the rate of radioactive decay. So decay is random and it is spontaneous. And so the only way that we can model radioactive decay is by modeling a very large number of decay events. And the analogy here is like rolling a dice or flicking a coin. I mean, I could roll a dice 4 times and get the same number. If I roll the dice 100 times, I am unlikely to get the same number. If I roll the dice an infinite number of times, I'm likely to get, let's say, a 4 1 in 6 times. And we don't see that 1 in 6 probability or that 1 in 2 probability for flicking a coin until we observe a very large number, i.e. close to an infinite number of events. Now, I don't know whether you've got this table or not. Apologies if you haven't. You'll just need to recreate it. You just need to be aware of the properties of the 4 radiation types. So let me just kind of go through some bits of it with you and link to some work that we've already done in earlier units. You know, don't you, that there are 3 materials that we use to distinguish between alpha, beta and gamma in terms of their penetrating ability. So we would say that alpha is stopped by paper, aluminium stops beta, and lead stops gamma. As we will see later, lead reduces gamma, and actually the increased thickness of lead decreases the amount of gamma that's able to be transmitted through it. But it's what we mean by beta, and in this context we mean beta minus. Aluminium stops beta minus. Now, the reason that we haven't included anything for beta plus being the positron, that is an antiparticle. You now know that when an antiparticle meets a particle, its corresponding particle, so in this case an electron, it's going to instantly annihilate and all of that mass is going to turn into energy. So in beta plus decay, that positron almost immediately finds an electron, and there are plenty of them generally around, and it annihilates, and so we don't detect that positron in the same way that we would an alpha, beta minus or gamma. Okay, so it's just you being mindful here that when we're talking about beta, we are generally referring to beta minus decay, the electron. Now, here's a nice link to the work that we've done on electric fields. So we've got a uniform electric field between these 2 parallel plates. So that can be determined by taking potential difference and dividing by the distance between the plate. We also know that the electric force is only felt on charged particles. Okay, so we would deduce then that this green dotted trajectory is the gamma because it's undeflected, so it cannot be experiencing an electric force, so it must have 0 charge. That's consistent with gamma. We can deduce, I guess, the sign of the charges followed by the 2 other paths. So this must be the alpha particle. Alpha particles are positively charged because they're 2 protons and 2 neutrons, and beta minus is negatively charged, and so they're going to go to the corresponding oppositely charged plates. Now, interestingly, the path followed is not symmetrical, is it? And I guess there are 2 reasons for that. Firstly, the charge on the alpha particle is different. So if we consider the force due only to the charge for a moment, the force on an alpha particle is twice that of the beta particle, because the alpha particle is 2 plus, the beta particle is 1 minus, so the alpha particle experiences twice the force. However, we can't ignore the fact that the mass is really different. And the mass of the alpha particle is tens of thousands of times that of the beta minus particle. Okay, so the mass of the beta particle is 9.11 times 10 to the minus 31 kilograms, and the mass of a proton or a neutron is 1.67 times 10 to the minus 26 kilograms. So there's a huge differential, isn't there, between the mass of these 2 particles. So therefore, when we're considering the acceleration of particles, It's the ratio of force to mass. And when we're considering the alpha particle, then it's got twice the force compared to the beta minus particle, but it's got 10,000 times or 10,000 times more mass. And that is the significant factor then. It's the mass that's important. And so therefore the beta particle accelerates more rapidly than the alpha particle. Okay, we could talk about this as well in terms of Newton's first law and inertia. The alpha particle has a significantly more inertia than the beta particle. So it is more unwilling to have its direction changed as a consequence. So nice link there then with the work on electric fields. What about magnetic fields? So we know that, again, only charged particles experience a magnetic force, and that's the BQV force. So the gamma carries on through undeflected, and by virtue of the opposite charges, beta and alpha are deflected in opposite directions. Now we know as well, don't we, that the magnetic force is always perpendicular to the direction of travel. And that was the condition for uniform circular motion. So the magnetic field is supplying a centripetal force. It's not affecting the speed of those particles, but it is affecting the direction that they are traveling in. They are following a circular path. So again, the difference in charge is determining the difference in trajectory. Okay, but we've also got that difference in mass. And again, that is the more significant factor here. So the acceleration of the alpha particle being far less than that of the beta particle. Hence the change in direction being significantly less for the alpha particle. In terms of why do they move in opposite directions, I guess we would use Fleming's left-hand rule, wouldn't we, to kind of predict that motion. And remember, current is the direction that a positive particle would move in. So the alpha particle is the positive particle. It's moving to the right. We've got a magnetic field directed in to the screen or to the paper, and therefore there's an upward force on that alpha particle and a corresponding downward force on the beta particle. Okay, and you can apply Fleming's left-hand rule to verify that for yourselves. Okay, so we know which particles are and are not affected by electric and magnetic fields. We know how far they travel. The other indicator we use for how far they travel is in air. How far would each of these things travel in air? And the word few is your friend here, okay? Because like how many is it? Is it 2, 3, 10? What is it? So if we use the word few, so for alpha, it's a few centimeters in air. Beta minus is a few meters in air. Gamma is a few kilometers in air. So the way that you would protect yourself from the harm caused by those three is going to look very different, isn't it? Take one step back from alpha, decay an alpha decaying substance, and you would be protected, but you would need to travel kilometers away from a gamma decaying substance to be protected in the same way. Obviously, with beta plus, we've already discussed this. It travels really no discernible distance at all. It's very close to a fraction of a millimeter in air before it annihilates with an electron. Okay, so the final thing then that we need to just look at is kind of ionizing properties, and the words that you've used at GCSE are these, and I would suggest that you use these again. Alpha is very strongly ionizing. Beta plus and beta minus are weakly ionizing, and gamma is very weakly ionizing. Now, what does ionizing actually mean? It means the removal of an electron from another atom. And the issue there is that you then generate quite a reactive atom. So an atom which has lost an electron has become more reactive, and that can trigger other reactions. And if we're talking about this in the context of the human body, some of those other chemical reactions can be quite unhelpful and unwanted. As well, if we look at the nucleus of the human cell containing the DNA, the bonds that hold that helix structure together get broken through ionizing events, and that damage to your DNA changes it. So we would call that a mutation, and that mutation can then be replicated, and that might ultimately lead to a very undesirable disease such as cancer. Okay, so why are the ionizing properties so different? It's by virtue of charge. So if you imagine an alpha particle coming along past a neutral atom, then it's a case of opposites attracting, isn't it? You've got this 2+ charge on the alpha particle, and it's literally going to rip an electron off from the outside shell of an atom. And it's going to do that quite strongly by virtue of its 2+ charge. Whereas beta, by virtue of its 1-, it's got half the charge, so the ionizing power is going to be much less. That's almost going to kind of push, it's going to repel an electron out of the shell of an atom. Okay, gamma being pure energy, well, the energy just has to be in the right place at the right time. And that's really challenging, because here's our gamma, it's just pure energy, and it has to be in the vicinity of that electron when that electron happens to be in that place in time. And of course, electrons are constantly in motion themselves. So for that gamma energy to be absorbed by that electron, that's a less likely event. And so that's the reason for gamma being very weakly ionizing. So if that were to happen, that electron ends up in an excited state, and it might be freed from that atom. Okay, so that's just a little tour through all of the properties then of your 4 radiation types. So your next job then is to populate that table with all of that information, and then the process of learning it. Okay, so you would be expected to learn that information. Now, for now, I'm happy for the mass to be expressed in terms of relative mass rather than atomic mass units. So, for example, when you do the alpha particle, you're going to say that it's got a relative mass of 4, and when you're doing beta minus, you're going to say it's got a relative mass of approximately 0. It's not 0, is it? It's about 1,860 times less than that of the neutron, but it's close enough, isn't it, to be considered 0. So that's your next job, to start populating that table.